Welcome to the third section. Let us see some more details about page tables. Now, so far what you have learned is about a page table which helps us in converting the page number into frame number. Now, what does the page table entries are? What are those entries? Indexed by using page number, getting the frame number out of it. Now, how many bits which are there to store the frame number depends on how many frames you have on your physical memory side, and how many page numbers that a particular table of a particular process would have. It depends on the size of the logical memory of a process. Remember, every process has its own page table, and each process has its own requirement on the logical memory side. It depends on how big your code is, how big your data is, and how much stack you need while the program is running. It all decides about your size of the process. And sometimes stack is not possible to be predicted, but OS provides it based on the need. But still, code and data will be known prior to the process starts running, because your executable size will be there, which will give you an indication of how much of process size is going to be, and based on that the logical memory size of the process would be decided. Then how many number of pages needed for that process will be known. Then you will have that many entries in your page table. So it actually all starts from the way we create an executable, and once the executable is created, based on the contents of your file and how much of data you have created in your program, your executable is created. Now once the executable is laid out, means when you have the entire program layout of your executable, that will be divided into code area, data area, and constant data, and initialized data and uninitialized data. Those things are all laid out. Then based on that, sizes will be decided, and your system will have either some 4 kilobyte of page size or 2 kilobyte of page size. Based on that, you will be mapping them to page size on the process logical memory side. Then you will know number of pages totally needed, and how many of them are needed for the code, how many pages are needed for the data. It all depends on the entire size of the executable as well as the size of each page that you have in your system. Now once this is decided, then page number will be known. Once page number is known, you will have clarity on how many entries are going to be there in the page table, because for every page number, which is a sequential number, you need to have an entry here. And inside the page table, we said that only frame number is going to be. Now I am going to add more entries to the page table, but till now we know that frame number is going to be there. In that case, for every index, how many bits are required in the page table? That depends on the frame number. Width of the frame number is decided by the physical memory size. What is the total size of the physical memory and how many frames are there, because this size will decide the frame size also. So number of frames will be known, and based on the number of frames, you will know the number of bits needed for the frame number, because if there are 16 frames, then you need 4 bits for storing them, right? Then the entries will be decided. So this is how the entire thing works. So far what you learned is about only page table having the frame number in it. Now let us see what are the other things we needed in a page table. Let us take an example of some process. Okay, it has got code, it has got some data, read-only data, okay, and then some data which is read-writable, and I have stack. Imagine there is a stack. Now what are the access permissions? I am just giving you access permissions of each of the different areas of the code, of the executable or a process. Executable is in term, when it starts running, it becomes a process. Executable is just a file. When it becomes a process, then it is ready to be executed. Now to become an executable for executable to become and process, OS needs to do some job of understanding, opening up the executable, understanding the different segments of code data in the executable, and make it into a laid out in a logical memory space based on the addresses decided by the linker, and you get the number of pages needed for the code and data and stack. And based on the constant data or not, you will have different things grouped here. Now imagine I am assuming that each of these different areas of a program takes only one page, whatever may be the page size you decide. Okay, it is independent of our is not dependent on our discussion. Take example of some page size and each of them is within the page. That's it. Now code is what access permission will have. It has to be read. Code is opcode which needs to be read by the CPU, so it should have a read permission, and it should be executable code. Okay, you cannot arbitrarily read some bit pattern and try to make the CPU run. CPU will say illegal opcode. So the code area should have read and executable permission. And constant data, let me say constant data, it should be only read only, because nothing else you can do. You can read the data and then you cannot modify it and write it back. And then some data can be read writable, and stack has to be read writable because you will be writing local variables, you will be creating, and parameters you will be passing, and the local variables you will be modifying. So it should be read and writable, because then it's keep changing when your function is called, and then you pop out things when the function returns. So you need different access permissions. Now since I said that each of the sizes of this code is mapped exactly to one page, how many entries will be there in a page table? I am going to draw little bigger than what it used to be. Okay. Now we are sure that frame number is one thing which needs to be there based on the size of the physical memory that we have. Finally, let us not bother about this now. We have understood that part of it much better. And then the number of entries here, because we have only 4 pages, let me say 0, 0, 0, 1, 1, 0, 1. That's it. Only 4 entries need to be there. Each of them, depending upon whether that particular page is there in the physical memory or not, that frame number will be mentioned here. Now, what are the other things you need? There are, let us go one by one. What about the code? Now, one thing we have to understand that each of these areas, those areas which have different access permissions, they need to be on different pages. Why? Because the entire control is done by the page table entry for a particular page. Now, page table is the like a gate. Like you have a theater, you have different seats, sitting arrangement. This is maybe theater means the farthest one will be the costliest one, and this screen is here. This is the cheapest one. So let us say cost is C1, C2, C3. You are paid this much money. So rows A to B, A to Z, A to D, and then some range of rows are given. Some cost. Now there is an entry, right? Main entry. Here the security sees whether you have a valid ticket for the show or not. It doesn't care whether you have which class of ticket. But finally, when you enter the theater, there may be different entry point, and person with C1 should be able to only enter this, and it can occupy only this area. C2 may be this area. So there is some control at the entry point. After you going there, maybe they will tell you the seat number and you are supposed to sit there. So there should be a control at the entry point, right? Similarly, where is the entry point for the addresses generated by the CPU? Page table, and the addresses are going to be again given to the physical memory later on after the conversion of the address. Now here there is no programmability. The physical memory is like a storage space. It will have some intelligence like error correction, and if suppose some data inside that particular location is corrupted, then there will be some error correction code, and it will make sure that it is valid or corrected. So those intelligence is there, but it cannot have much more than what it can be implemented in a hardware. Now, since we have a common type of memory which is DRAM, which is read-writable across, any part of the memory should be read and writable. That is why you are able to bring any page into this. OS is able to write into main memory at any location. It's able to write. So it has a write permission one during the transfer of pages. But once the page is put in the main memory and the CPU starts executing the code on behalf of those processes, they need to have a different mechanisms, control mechanisms, such that even though a particular part of memory currently is anything, any part of the DRAM is read and writable, if there is a code in it and the CPU is trying to access the code area, it should have only read and executable permission. Though the physical memory technology as such allows you to read and write and do whatever you want, we are using that part of the memory during the time when the code is residing there only to do a read and executable permission. To have valid access of that memory becomes only that much, right? So who can do it? The page table only can do it. In that case, what should the page table do? It should store the access permissions. So there are additional bits reserved for whether it is permission or it has got a write permission and executable permission. It's similar to what you have at the file level in the Linux file directory for different users. Here we have for every page this read and write executable permissions. Then you need one bit for each of them. You don't know particular entry is going to have code part being mapped to that, or maybe data part or a constant data part, we don't know. So all the access permission bits should be there for every page level entry, and based on a particular situation where they now in our case code is here and data is here, whereas suppose in another process is there, it will have another page table, maybe code is occupying the first two entries. So the page table configuration or the structure of a page table should accommodate all kinds of access permissions that can be allowed in a page, should be there for every entry, every page entry. So these are the bits that we need. Now if we map a code for the this side of the address maps the type of page that you are going to be accessing, and this side decides which frame you are going to access. So the entry side, when a page access is happening, it could be that PC is accessing, program counter is accessing a code area, then it will generate a address which will come here. Whereas if some data transfer is happening, it is for read permission. For read access, it will be load instruction. If it is a write access, it will be a store instruction. So whatever may be the instruction being executed, based on the execution, whether it is coming from the program counter register or is it coming from any normal data register, address registers, you will have different access permissions built into the address itself, because uh, based on the instruction you will know what type of access it is, and based on the address it is accessing, you will know whether it is accessing this area for executing or this area of the address it is trying to write into or read into. So this is decided by the programmer or the tool jointly, and the generation of address is happening while the program is executing. During the generation of the execution, based on the mapping of a particular page to a frame, these bits are already set, because you know whether you are mapping a code area to this entry or data is mapped to this page or not. So these entries are already fixed by the OS before the process starts. Any page is loaded in the, any pages has to be brought into the physical memory. It is updated and then brought here. See, the thing is, executable is read and the decision is taken to bring a particular page into the physical memory. Only when you bring the particular page into your physical memory, you need a entry in the page table. Though there is space for each of them, only those pages which are currently being in use, which are being used, are having an entry in the page table. Other things will be there, space will be reserved for it, but it will have an invalid entry for a frame number, which means that even that page is not there in the main memory itself, there is no relevance to the read and write of executable permission. So how do you know whether you need to look into these bits or not? Because it can be either 0 or 1 state, right? The read and write executable permission. So there should be a way you need to have a valid bit, okay? Because even the frame number is, all the bit patterns are valid. 000 to 111, whatever may be the bit of the frame number is valid. So here RWX is also all combination of 1 and 0 is valid. In that case, you will not know whether a particular entry is having a valid entry or not. A page table index, if suppose you are indexing into it, either it has a valid entry or not, you will not know, because every bit pattern in that entry can be a valid value. So there should be another bit position within the page table to indicate whether you should look into the content or not. Because all zeros is also a valid entry, all ones also could be a valid entry. So only this valid bit will decide. If it is 0, don't even look into the contents. If it is 1, yes, any entry is a valid entry. Okay. There may be some corner cases where some combination is not a valid entry, but I'm just saying that for our discussion purpose, it is a valid one, because you can have all access permissions could be given. I'm saying that RWX is not a valid combination anyway, because no part of the, unless it is a self-modifying code where that self-modifying code can be writable, it has to be readable because code has to be read before executing it, and it is executable because that's a code area. So RWX, all bits could be set only when it's a self-modifying code, but which we are not actually talking about it. So you need a valid bit. If it is 0, that particular entry of the page table is not valid at all. If it is 1, it's a valid one. So now this much you have understood. The sequence is, let me summarize it. Executable is there in the hard disk, and the program is going to start. So the basic need of the whatever may be the start of the code, main area, that code area is brought, and some data area, whatever is needed, is brought into the main memory, and then the program starts. Or maybe data can be delayed until the program tries to access a particular data area. That could be delayed also, but I'm just saying that maybe I will bring one page of each of those different segments into the main memory, which may not be correct because it depends on the program sequence, whether it is accessing in what sequence. Anyway, so for a executable to be becoming a process, you need to have the basic code and data loaded here, and those entries are to be made into the page table, and the valid bit needs to be set, and the program starts running. This should be scheduled on the CPU and it runs. Then when it runs, it generates an address and it accesses the page table entry, and that page is mapped to a particular frame. It goes ahead and accesses the program and starts running. Now you are understood about the valid bit, read writable executable permissions, and I am going to say something more. I told you that the process memory, whatever is the logical memory, is much bigger than the physical memory available. Okay, and only some part of the code is brought initially to run, and even the data is only what is needed is brought. Now, what if I am trying to access an array of 10,000 elements? I have brought maybe 100,000 elements, and I have brought the initial maybe 1,000 elements. Now I am crossing that limit. When will I know? When I am maybe loading the data, LDR I am doing, and then maybe I have a R1 register holding the address, and I am loading the value of that content at that address into R0. I am executing this instruction on the CPU side, and R1 is the address which is accessing the 1001 byte. Okay, it's not 1001 byte, 1001 element, which could be multiple of 4 or 8 or whatever, or it could be a character also, doesn't matter. I am trying to access that particular address, which is not there currently in the physical memory. Now that 1000 address would map to some entry in the page table, you agree? And then the valid bit, what I said, that would have been 0. Frame number is invalid and all other entries are invalid. Now, when this happens, what should the OS do? Can it stop this execution and then say that the process is made an illegal access because it is trying to access a page which is not there in the physical memory? No. From the process perspective, it is accessing within its own range. It is accessing a valid value. The problem is with the OS, which is not brought all the 10,000 elements into the physical memory because it doesn't have. So, when an address is generated, and which is a valid address, of course, which is within the address space of the process, so it has a valid entry in the page table, but the page table entry valid is 0. It's not mapped to any frame. That is what is called page fault. It's a fault, but it is not the fault made by our software. Our software is running fine. It is a problem because OS has not done the job which it guaranteed that it will do. It said that I will take care of all your area, data area, the code area you want. So I built the executable, I want to run it. But now you say that my code generated a page fault, which is not my fault. Yes, it's not the process fault. It's a fault which is to be addressed by the OS. How does it do? It needs to bring the page into the physical memory. Now, where is it now? You have already executable is there, correct? That is in the hard disk, and a page what you are looking for could be would have been already used, or it could be opened up and kept in a process is running now. So it depends on the how the particular OS is managing it. Imagine that page is there in the physical hard disk. Okay. If it is first time accessed, it would have been initialized to some value what it was done by the programmer. But if it is after the program has run for a while, it may be a modified value. But I will come to that now. Assume that it is the first time you are accessing the 1001 location, which is there in the hard disk, which needs to be brought into physical memory. Now, let us imagine a situation where physical memory is entire thing is occupied. It's all full. There is no place. Now, I can't tell the process that I'm sorry, you generated a page fault, but I don't have space in main memory, so you are not allowed to run. I am going to kill that process, which is not correct. Even if it is a low priority process, it has not done anything wrong other than asking for accessing its own data area, which is not there in the physical memory, is not its fault. So what does the OS do? It will look for a page which is a frame or a page of a particular process which has to be evicted. When I say evicted, it should create a free space in the frame. One frame, because it has to bring one data area into one frame. So how does it decide? It depends on the page replacement policy that we'll talk about it later. But it has to pick one victim page. I call it as a victim page because there's going to be a victim which is going to be evicted. And remember, the victim page need not be the page belonging to the same process. You cannot say that you wanted extra page, I am going to remove your own page. No, it's not a tit for tat kind of a fight with the process. OS is very gentle and it will pick a process which is not currently needed to be in the main memory. That means it may be blocked, it may be waiting for some event, or it is much lower priority than the process which is currently asking for a page. It could be any reason. Okay, you can imagine that some page is picked up which is not an active page which is being used currently by another process from another core. Please remember, there are multiple cores available and they are all be accessing the same physical memory. So you cannot just to create one page for a core 1, you cannot remove a page which is being accessed by the core 0. So that information should also be there and you should not pick that page as a victim page. So that OS is aware of. So it picks something which is not being in use, which is not currently being used, but it may be that the process is in some state, but it's not in the running state, of course. Okay, so that page is picked up and you need to make sure that this page is belonging to which process, right? So as I told you, the page tables are maintained process wise and the process ID is associated with the page table, and it will be known to the OS. It is maintaining the page table entries per process in its own data structure, and it also knows which frame is being picked up and where this frame is mapped to which page table. It could be belonging to any process, and then it goes into that process area, and it goes into the page table entry of that page and looks at whether that particular page was changed or not. Now I am going to bring one more bit into the page table entry, which is called modified bit or a dirty bit. So apart from read write executable and valid bit and frame number, we are going to have modified bit or a dirty bit. Now what does it mean? Initially a page is brought into the main memory where the modified bit will be 0. Okay, because first time I'm bringing it, it's not changed, it's a fresh page. Now you start running the program and some data gets changed here, okay, which is changed in the main memory. I told you that there is a copy maintained in the hard disk. That whatever copy is there in the hard disk is not changed. Every time you cannot go to the hard disk and make changes. It is done in the main memory itself, because you know that it is very expensive to go to a hard disk to make a change. So, and you cannot do a bitwise changes or a bytewise changes. You have to do a block movement because a hard disk is a block device. So, byte access is possible in the main memory. So, you can modify one character of your array and it will be reflected in the page or a page which is mapped to a frame. Now, there is after these changes that process is blocked and then it is modified bit is set, and now imagine that that was a process P2 which is picked up a frame which is holding a page of a process P2 is picked up for creating a space for our another process P1, because you have to bring that 1001 into the frame. You need to vacate it. Now the victim page has already been modified. I am using the page and frame alternatively. Imagine when I am saying that I am referring to something page is residing in a frame, still it's a page only, but it is in the frame of a physical memory. So it is modified. Now if I overwrite a page belonging to some other process P1 into this same area, the previous content is erased, and whatever modification done by the P2 process when it was running is completely gone. Now next time if I am bringing the same page from the hard disk, it will be different from what it was there in the main memory, which is totally wrong. Now am I doing something wrong as a OS? Yes, you are, because process is assuming that it has got all the memory it wanted and it was modifying something and it went into a block state for some reason. That doesn't mean that you should wipe out the data that it was holding. You need to take care that even though the process is sleeping and it is going to wake up and come again and execute, it wants to see the same data it had seen before it went to sleep. So you need to take care of that as a OS. So what should I do? I need to copy this date page, entire page. Now why should I entire page? Why can't I change just this particular byte into this? First of all, block device doesn't allow you to change only one byte. That is not the reason altogether, but you cannot be sure or you cannot keep track of which byte in a page has been modified or a frame is modified. Then you have to have that many number of bits, which is your page table entry will be as big as the frame size, right? Then you cannot track at the byte level which was modified, and it's not possible. So anything which is changed, even one byte or one bit is modified, that dirty bit will be set. If the dirty bit is set, I will not know when I am evicting a particular frame or a page from the physical memory. I will not know which bit was modified. I have to write back the entire stuff. So when you want to evict, if that particular page entry, page table entry has a modified bit set, then it is the responsibility of the OS to write back this old content, entire old content into the area belonging to the process P2 somewhere in the hard disk. Write it. Now when I say write it, this memory is copied, written into the hard disk. It may have the old content still there. It's not that I am going to wipe it up with zeros. There is a waste of energy, right? Waste of power. I'm going to now bring a new page into that area. Whose page? P1's page. So I will be anyway overwriting it. I don't have to again clean it up and then bring it. It's a waste. So it is not done. You bring a new page. And then what should I do? I have to make the entry. Now suppose frame number is 10. I make the frame number value as 10. And then if I am bringing the data area and if it is read writable, then I have to make the read writable permissions as 1 1. Executable permission, of course, data area doesn't have, so I have to make it 0. So RW will be 1. Now X will be 0. And then valid bit will be 1. So I have made that entry. Paka, perfect. Now is the job done? What happened when the process wanted to execute this instruction? The address it put in on the bus and page fault happened and the OS stopped the process. Okay, it will be in a block state. Okay, it can't be in a ready state because it's not ready to run because that page what it wants is not available. So it can't be in a running state. Of course, it's not running now. Right now it is running, but it's going to be evicted from the CPU and the OS is going to run in place of the process, and it's going to do the job of bringing the page to the main memory. Before that, it found that there is a page which is it identified a frame which is to be evicted. It ran a page replacement policy and found out a victim page, and then it found that the victim page happens to be belonging to some other process, and it is its dirty bit is set by looking into the page table of that P2 entry, and now it has to write back that it has gone in written back, and then it went into hard disk of P1 area, brought that page into the same place and updated the frame number. Everything is done now, but still it needs to take care of one more thing. What was the instruction which caused the page fault? That PC is pointing at the address of the instruction address, not the address which is being accessed. It has to execute the same instruction again now because it did not execute this instruction at all and page fault came. What is the impact of not executing this instruction after the page fault? In that case, what will happen is R0 will not have a valid value from this location. Then if I do add R0, 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 what will happen? I will not be using the content which I read from 1001. I will be using some other content which was there prior to this and adding it. So the program sequence, entire sequence will go wrong. So I have to guarantee that the program runs correctly, even though I do lot many things in the background to make sure that multiple processes running in the system. OS is doing all this, but OS also has a important responsibility to make sure that the process runs correctly. So it will execute the same instruction again, which caused the page fault. Now what will happen when it executes it? 1001 address will be put again. It will come, there is a valid entry, valid bit is there, and the frame number is initialized, so it goes to the memory. Now it will see that the 1001 at location is not here, it is somewhere here, suppose because victim page is identified here, so it will read back that content and it will continue further. So this is what happens page fault when page fault is happening. I hope this is clear to you now. So to summarize, a page table entry has become longer now for us. Apart from the frame number, we have read bit, write bit and executable bit, then modified bit. And of course, valid bit is there to start with. So is there anything else I need at this moment? No. This is what we are going to be happy with. And this we already know. This also now you know. So now what I will do, I will run through, I think page fault is understood, and page replacement policy is understood, and page table per process is also understood, and you have entry for every page of a logical memory in the page table of its own, and the entry in that will be valid bit has to be 1 to look into the contents of that page table, and entire thing will be fine. Now let us just quickly run through these slides for a completion sake. Okay, page fault. because of the growth of software and machine learning algorithms coming up with lot of models with a huge number of weights, your logical memory size is going to be bigger. So many pages are going to be there and those pages are to be in the memory. So whenever it needs, and if it is not there currently, page fault is generated, and this particular feature is called demand paging, that when the program needs a page, it is brought into the physical memory. Now what is the need for this particular thing? Because based on the control flow of your program, you may not touch all the part of the code, and if you don't touch all the part of the code, maybe you may not touch all the part of the data which is accessed by those part of the code, so which you don't know when before the program starts. So it is not worthwhile to bring all the pages of code, data, stack, everything into the main memory, because it's a waste of bringing from the hard disk to the main memory. And not only that, you are taking more time to load your program, it also occupies a lot of space in the main memory, which will not give space for other processes to run, because the physical memory is shared by other processes. So you bring whatever is needed to start with, and then you keep bringing the pages based on the need. That's called demand paging. And what are the access permission? Code is read and write, executable, sorry. Modified viable data is read and write, constant data is read, stack is always read and write, and heap is also read and write, because you are getting the memory from the malloc routine, not to just look at it and then enjoy what is there in it, right? You need to write into it. Unless you are able to write into the heap memory that you are getting, there is no use of having that memory. So it has to be read and writable. So these are the different access permissions which are part of the page table entry based on what page is being referred, what is mapped to a particular entry in the page table. Okay. Now this is understood by you. Okay. I'll tell you the control bits are this, frame number is this, and modified bit is there, and read permission is there. Okay. Now there are, what does the current page table pointer? Its page table pointer is actually referring to a particular, if I assume that this is the start of the page table, and then you add the page number to get the offset into the page table to index into it. So this is what answer is. Now what is the size of frame size? Now frame size is nothing but the offset size, right? Now 10 bits corresponds to 1024 to power 10. So 12 is 4 into 2 power 10. So 12 bits, 2 more bits are there. That means every 2 bit you will have 2 power 2, 4 combinations. So 4 into 1024, which is 4 kilobyte. And 4096. Maximum number of pages possible. Maximum number of pages is decided by this part of it, right? Because every bit pattern need to have an entry here. Okay. We saw from the small example that we had, you can expand it to 20 bits now. So 2 power 20 entries have to be there. Okay. So it may look very large for you. 2 power 20 entries for page table. It's a huge. We are going to see some way of reducing the page table entries by having multi-level pages. But right now we have only single page table, single level paging. So entire 20 bits is indexed into the page table. So it is 2 power 20 entries. What is the virtual memory space? You need to add both of them, because 2 power 20 into 4 kilobyte of size is the total virtual address space. So you have to add 20 plus 12, 2 power 32, 4 GB. Okay. Fine. Now what is the total physical memory? I said that frame number is 10 bits. Okay. And the physical address depends on the frame number. Offset is anyway 4 kilobyte is known. 10 bits is the frame number. So now what is the physical memory size? You can get it from here, right? Because 10 bits you are going to append it with the 12 bits that you have as an offset. So very simple. It is 10 plus 12, 22, right? So 2 power 22 will be the size of the physical memory, right? So whatever may be the value. Okay. Now every page will have a read write permission. Present bit is like a valid bit. Okay, present bit is nothing but valid bit. Either you can call it as a present bit or a valid bit. Okay, both are same. Don't think that there will be a valid bit as well as present bit. Valid means that the page is a valid entry is valid. If I say that a page table entry is valid, that means that page is mapped to some frame. That means it is present in the physical memory. So it is same as present bit or a valid bit. Two, I'm giving both because some literature will talk about valid bit, some books will mean the same bit as a present bit. Modified bit, dirty bit could be two different names again, and I have explained it already. So now let us look at one more example, which I am just going to go much faster. Okay, I'm not going to even explain it, which is self-explanatory. You need to maybe slow down and then get the answer and try to guess it. Okay, fine. This very easy. You will be able to do it. Fine. Now some more questions. What is used to index into the page table? Page number. What does the present bit mean? It means whether that particular page is there in the main memory or not. If a page is not in memory, what will it be? Where will it be? It will be in the hard disk. How is it certain that all pages in the PT exist? Because it is a range of addresses that are already told by the process that it wants it. So it needs to be there. Maybe some holes may be there. I'm not saying that all the logical memory space needs to be there, because what happen is some code area will be there, and then for convenience purpose data will be put in some starting address from here. So there may be some holes in the logical memory space. Then there may not be a valid entry in the page table. What happens, and if there is no harm in not having an entry in the page table, because that particular address will never be generated. Okay, that is also possible. What happens when a particular page is not in main memory? It has to be brought, page fault is done, and then the process is put in a block state, and everything is I already explained it. So then later on what will happen is that process is ready to run, but it cannot be made to run immediately because scheduler has to decide. That's the responsibility of the scheduler logic. So it will be put in a ready state. And never, you have to connect with the state transition, where from the block state any process would not move into running state directly. It will go to the ready state. Then scheduler picks up that process to run it. So when it is in ready state, that means that that page is valid and the entry is valid, and if it is going to generate an address, it is going to create, not to create a page fault, it is going to be able to run it. Maybe after some time it may create another page fault. It doesn't don't guarantee that always it will be running forever, right? Page fault will come based on what address you are accessing. Maybe one array is there in some location, and then immediately next instruction is accessing some other array which is not even in this particular page, and it's far away from another page, and that page is not in the main memory. So that is possible. Page fault can come multiple times within the execution of a page itself. It depends on what are you trying to do. But whenever a page fault is happening, if it is a valid access, then it will be brought and then the execution will be starting. Now suppose if you do a wrong pointer initialization, or you don't initialize a pointer and try to access it, that also will create a fault. But it's not a page fault, it's a segmentation fault, because that page address, whatever you have, is not mapped into the page table, and it doesn't have a valid entry in the page table, whatever address generated by you because of a wrong pointer. Then it is a segmentation fault. It is not within the logical memory space of a process. Then OS cannot do anything. You have done something wrong. If you are accessing something and it is creating a page fault, it is a proper problem created by the OS. Then it will take care of it. But if it is a illegal access and you are trying to create an address, access an address which is not even within your range, then it's not a OS problem, it's a program problem. Then it will say that it's a segmentation fault and terminate the process. So now page replacement thing, which I have already explained, it will identify some victim page, and then if the modified bit of that is already set, it will victim page will be written back. And then I want you to read through this one by one, because which has already been discussed. I don't want to repeat in the discussion. So bit will be a replacement step which is explained here. Then should the OS always write back the victim page? No, it need not have to write back every page. If it is a code area or a data area, read only data area, the page wouldn't have been modified. If it's a valid thing, right? Read only data shouldn't have been modified. Even if the process tried to do that, it would have created a segmentation fault and gone. So nobody could have changed it. So you don't have to write back because what the content in the hard disk and what is there in the main memory are the same. So you don't need to spend time in copying back to the hard disk. You can now overwrite with some any page that you are bringing in. So that's how OS tries to think of optimum way of doing things. Dirty bit is set, it needs to write back. And present bit is, and then you update the present bit so that when next time when the address is generated by the process, it will see that entry is present. Then it will go and look at the frame number and try to go to the main memory and access it. Okay, and OS needs to know what should it do. It cannot just make it run, it has to make it ready state, and then the scheduler will schedule it again. Then the same instruction, which when it gets a process allocated, CPU allocated to it, then it will run the same instruction. Then the instruction which caused the page fault will run, and this time it is not going to create a page fault, it is going to have a valid entry in the page table. So it will go and access the page and it will continue further until either program terminates or it generates another page fault. Okay, so this is how the entire process works. If you have understood this, you will know why there are these page table entries are, where they are getting accessed, how the OS is modifying them and setting it up for your program to run. And it shares the areas with all the processes, the main memory area, but still everything works fine and the process is happy, OS is happy, and all the processes running in the system are also happy. So that's the job of OS, and I hope this was useful. See you in the next lecture. Bye bye.